예, 안녕하세요. 이제 우리가 이제 한 학기의 이제 결승점, 끝나는 그런 시기를, 이제 뭐 그럭저럭 맞이하게 되었습니다. 사실 쉽지는 않은 학기라고 이제 할 수 있겠는데요. 어쨌든 여러분들도 이제 온라인으로 이제 수업을 들어야 되고, 저도 이제 온라인으로 이제 수업을 준비를 해야 되는 그런, 뭐랄까, 이제 평소와는 이제 다른 그런 환경에서 이제 뭐 강의도 제공되고 강의도 들어야 되는 뭐 그런 학기가 되었었죠. 사실 뭐 온라인으로 듣는다는 것이 이제 그렇게 쉽지 않은 것이라는 걸 이제 뭐 저도 이해를 하고 있습니다. 아무래도 이제 사람이라는 것이 그 피지컬한 그런 월드에서 우리가 이제 버추얼 월드랑 이제 피지컬 월드는 다르죠. 근데 뭐 우리는 이제 사실은 이제 피지컬 월드에 이제 사는 그런 사람들이고요. 뭐 그렇기 때문에 이런 환경이 좀 뒷받침되지 않으면은 좀 어려운 그런, 뭐랄까, 뭐 무엇인가를 하기가 이제 어려운 뭐 그런 뭐 존재들이죠. 뭐 그렇지만은 상황인 만큼 우리가 이 시기를 건강하게 이제 넘어가기 위해서 뭐 서로 이제 노력을 다 해왔고요. 사실 그래가지고 뭐 저도 이제 여러분 얼굴을 이제 한 번도 못 보는 그런 사태가 지금 생기는 것 같은데, 어쨌든 이제 기말 때 이제 처음 얼굴을 뭐 볼 수 있을 것 같습니다. 뭐 그렇지만 이제 다들 마스크는 이제 써야 되고요. 그래서 마스크 쓴 얼굴을 이제 마지막에 이제 볼 수 있을 것 같네요. 어쨌든 우리가 이제 두 번의 이제 강의가 남았고요. 그 두 번 강의가 끝난 이후에 이제 기말고사를 이제 보게 되겠고, 그리고 이제 숙제가 나왔죠. 숙제는 이제 메모리 시스템에 대한, 그러니까 메모리 하이어러키에 대한 그런 숙제가 이제 나왔는데, 역시나 이제 메모리 하이어러키는 이제 중요한 부분입니다. 그렇기 때문에 숙제를 잘 이해를 해서 이제 풀면은 뭐 좋겠습니다. 그리고 이제 기말은 뭐 문제 수준은 거의 이제 그 홀마크 수준으로 이제 나올 거고요. 저는 뭐 그렇게 믿고 있습니다. 그러니까는 뭐 만들다 보면은 좀 더 어려운 문제가 나올 수도 있긴 하겠지만, 뭐 그래도 이제 거의 홀마크 수준의 이제 문제가 나올 것이다. 뭐 그렇게 예상을 하면 되겠습니다. 그래서 홀마크를 이제 스스로 풀 줄 알게 된다고 하면은 그런 기말을 푸는 거는 그렇게 어렵지 않을 것이라고 생각합니다. So we have two classes, including this class, today's class. So we are finalizing the spring semester. So I know that this is not an easy situation because of COVID-19 pandemic. Yeah, I understand. So it is not easy to watch the online classes because it is difficult to focus on the lectures. Yeah, but in order to secure your healthy life and then some other people's health, it is the required process. So we will have a final exam on the June 22nd. Actually, it will take 2 hours for the exam, and then the difficulty level of the final exam will be similar to the difficulty level of homework assignment. And then so I believe that if you can solve the homework questions by yourself, then it's not difficult to solve the final exam questions. So, and then no electric devices are allowed during the final exam, and then you need to wear masks to prevent the infection from some other COVID-19. Also, yeah, so I will post some, what is that? So 방역 지침 for the COVID-19 for the final exam. Okay. So in this, so we have two classes, including this today, including today's class. So we are done on the chapter 5, the memory hierarchy. So as I said, memory hierarchy is an important topic in the undergraduate computer architecture course, and then also the memory is a very important component in the computer system. So as I said, the performance of the memory system decides the entire performance of computer systems. So it is because the data should be read from the memory. So actually in the programmer's view, the every data exists on main memory. So main memory is the DRAM. So you may think that our own data exists on storage devices, but in the computer system, the data on the storage device is transferred to the main memory, and then the programmer write the code to read this data from the main memory, and then do something with this fetched data. And then why do we need memory hierarchy? Because we don't have ideal memory. So what is the ideal memory? Fast and large memory. But this type of memory does not exist in the real world, in the physical world. So we use the memory hierarchy. And unfortunately, most of the application exhibit the data locality, and actually it is also true in our real life. So our real life has the locality too. So memory hierarchy exploit this locality to increase the performance of memory systems. So in the previous class, we learned about the TLB, the translate the leukocyte buffer, and then this TLB is the just a cache for the page table entry. So I said that the page table exists on the main memory, so DRAM. So now you know that if the program code wants to read some data from the main memory, then it will take a very long time. But I said that the program used the virtual addresses, but the data is stored in the main memory pointed by physical address. This is the real world address. So this virtual address should be translated into the physical address, and then this mapping information exists on the page table. This is some software structure stored in the main memory. The operating system manages this page table. So in order to translate this virtual address to the physical address, this is the real address in the physical computer systems. So for this translation, the page tables to be read from the main memory, and that is inefficient. So we already know that it will take a very long time to fetch data from the main memory. So in order to translate this virtual address to the physical address, then it will take a very long time, and this is not preferable in the computer system. So we can use the locality of page table, and then fortunately and then obviously the page table has the strong locality. So because the page size is 4 kilobyte normally, and then some page has the larger size. So you may think, oh, just 4 kilobyte, but this 4 kilobyte is very large in the view of the application or some normal program. So yeah, believe me. so this page table has the strong locality. So if the page table entry can be cached on the some on-chip memory of the computer system, on-chip memory of a processor, then we can improve the performance, because the page table can be read from the on-chip memory, the TLB, translate local side buffer. Okay, so you need to understand how this TLB works in the computer process. TLB is the computer hardware. The page table is managed by operating system, but TLB is the computer hardware, so hardware of the computer processor. And then in the previous class, I summarized some concept of memory hierarchy and then cache configurations. Also, I briefly mentioned cache coherence. Actually, this cache coherence and then actually memory coherence and then memory consistency issue is critical for the parallel processor, which have the multiple cores or multiple update processing engine in a single chip. So, but that is actually this data memory consistency and the memory coherence is a little bit difficult topic. So it will not be covered in I briefly explained, but it was not thoroughly covered in this undergraduate course. Okay, so I mentioned the parallel processors. So this chapter, so we will learn about this parallel processor. So this is also some difficult topic. So you may think, oh, it's just the parallel processor. What's wrong? But this is the difficult topic. So actually, in this course, I will briefly explain about this parallel processor architecture. But detailed architecture will be taught in some advanced course or in the graduate course of the computer architecture. Okay. So I believe most of you are very familiar with the parallel processor, because most of a modern processor has the parallel processor architecture. That's true. So if you see your smartphone, and then smartphone has also CPUs, and then recently modern smartphone has the multi-core architecture, and then multi-core architecture processor and very large DRAM. So for example, the flagship smartphone of Samsung Electronics has the I don't know the exact number of cores in a application processor equipped in the Samsung Galaxy smartphone, but I believe it's more than 4, right? I don't remember. I don't have any Galaxy smartphones. So that means that the mobile processor also has multiple cores in a single chip. And how about the memory system? The DRAM size of the flagship smartphone is about 4 GB recently, and then the expensive smartphone has the 6 GB or 8 GB of memory, DRAM memory. It's very large actually. So, and then for normally in some budget level laptop has the memory has the DRAM size of 4 GB recently, but it was 2 GB in a few years ago. So actually the 4 GB, 6 GB, but even 8 GB is a very large size of DRAM memory in the mobile phone, actually mobile devices. But even the mobile devices has the multi-core architecture, and then also very large size of memory. For what? High performance. And then actually for your laptop or even desktop, then I believe most of people are using the laptop computers, because this is the mobile era. So How about the mobile this CPU processors equipped on the laptop computers? It's also the CPU has multiple cores. Like for example, i7 has the 6 cores, right? And then the i5 has the 4 cores. So it's the multiple cores. Now, what is the core? Core is the independent processor. So we learned in the discourse. So we learned about the independent processor. So actually, this is the very simple processor. Has the pipeline that has the pipeline architecture, but this is the independent processor. So core means actually core is equivalent to the independent processor plus private caches, such as the L1 caches or even L2 caches. So and then for Intel multi-core processor, a single core has an L1 instruction cache, and then L1 data cache, and then L2 private cache. So this independent processor unit is called the core. So actually, with this single core, can do everything. So that means that this single core runs the independent application, or this is called the thread. So it's a process. So this independent, so it's the single core can run independent thread process application. So and then what is the advantage of parallel processors? So it is similar to the multiple worker, like so let's think about this one. There are only one worker. So one worker. So one worker do this amount of workload is some what's that task? It's a task per day. And then so we want to increase the amount of tasks processed by workers. So what is the some available ideas? What are the available ideas to increase the number of amount of tasks processed within the same time? The simple idea is to increase the number of workers. So it's not always true, but we think that if we hire more workers, then we can make more the large amount of tasks can be processed within the same time. So if we hire 4 workers, then if the 4 workers work in the same rate, then what is the expectation? The 4 times of tasks can be done in a single day. And then that is also some what's that similar expectation for the multi-core processors. The multi-core processor has multiple cores. That means the multiple processors. So with these multiple cores, then more work, or this is called the tasks, or called some thread, or called the workload. So more tasks or more thread or larger amount of workload can be done within the same time. That is our expectation for parallel processors in the multiple cores. So in this chapter, we will learn about this technique, this architecture. So introduction, I already explained about introduce the parallel processors. Then what is the goal of this parallel processor? We can use the multiple computers or multiple processors to get higher performance. What is this performance? This performance means the amount of workload. So it's related to the throughput. of tasks. So by using multiple cores, our expectation is that we can increase the amount of tasks or workload processed by the single CPU chip. So this is the advantage, actually the expectation and then advantage of parallel processors, but it's not always true. And then we will learn why in this chapter. So this is the we can use the multiprocessors, the multiple cores, but the issues are scalability, then availability, and then power efficiency. These are the issues we need to tackle in the multi-core architecture or parallel processor architecture. So what is the scalability? I think you can understand the availability and then power efficiency of the processor, but what is the scalability? So this is our expectation. So if the same task is done by the one man, one worker, then we assume that the task size 1 can be done in per day. But if the two people work concurrently, it ends up in parallel. The concurrently means in parallel. Then what's our expectation? Double of tasks can be done per day. That's our expectation. But is it true in the real world? No, it's not true. Why? Because of the communication burden or some other issues, such as order of the jobs. So for some jobs, A should be done before doing the job B, task B. So this is the order of job. But if this job is not parallelizable, cannot be done in parallel, then there is no benefit with the two workers, the multiple workers. So there are many issues to reduce the scalability, to hinder scalability. So this is called the scalability issue. So if the amount of tasks done by the multiple workers or multiple cores is similar to the number of workers or number of cores, then it is told that this processor has the scalability. But it's not true in the real world. So we already know, but we do not agree with this situation. Normally the boss, most of the bosses do not agree with this situation, but it's true in the real world. If we invest more workers, more cores, but the performance is not doubled, performance is not proportional to the number of workers because of the communication burden or some characteristics of workload. So actually this is very simple with the multi-core processor. Task level parallelism. So that means that we can increase the number of tasks. We can increase the number of independent thread that runs on the multiple core. So if there are many tasks, many independent, I said that independent, there are many independent tasks or there are many independent threads running on the some computer system, then multi-core processor will be very helpful. So the operating system just assigned this single task or single thread on the each core, and then this core will run this independent thread, and done. It's actually a good situation. And then also, so many people said that the multi-core processor is good for the multitasking. So multitasking means that multiple thread runs concurrently on the computer system. But for the single thread or single application, this we need to we need to do something to increase the performance of a single thread on the multi-core architecture. The parallel processing program that runs the single program, but this single program runs on the multiple processor. Then how can we increase the performance of this single program? We need to apply the parallel algorithm. Okay, that's very important in the software design. Okay, software design, application design, and that runs on the multi-core processor. So recently, one application is split into multiple thread to exploit the performance of the multi-core architecture. So that's, but for the single kernel, or single application, such as the matrix multiplication. So matrix multiplication handles the multiple element, but how can we run this matrix multiplication application on the multi-core architecture? That's the research issues, and then actually the mathematics or computer science researchers need to work on these issues: the scalability of the software or scalability of the computer system. And then multi-core microprocessor is there are multiple processors or core in a single chip, and then this architecture is called the chip multiprocessor. So this is the example. The example of the serial processor was single core processor. It's called the single core processor. It's a Pentium 4. So have you heard about the Pentium 4, or have you used this Pentium 4 on your computer system? It's a very old generation processor developed by Intel, and then Pentium 4 has the single core. That means there are only one core in a single chip. And then what is the example of the parallel processor or multi-core processors? It's a quad-core Xeon. Just a quad-core? Xeon has just a quad-core. Actually, yeah. So recently, the Xeon has the tens of cores, and then even the desktop or some laptop CPUs, such as the Core i3, i5, i7 has the multiple cores. This is also an example of the multi-core architecture or parallel processors. Okay, and then let's see the software, and then the example of the sequential application is the matrix multiplication, which we are very familiar with this application, because we use this matrix multiplication as examples frequently. And then what is the example of concurrent software, like parallel software? Operating systems. Operating system runs the multiple process on multiple thread, and then this multiple thread can run on the multi-core processor. This is the example of concurrent software. So actually, these different types of software runs on the same computer system, like a serial or parallel hardware. So what is our challenge? Scalability. So making effective use of parallel hardware. So what is the some challenge of the multiple workers or many people? If this many people works on in the same department or 부서 department, performance and scalability. So that is the challenge of software and computer system. Okay, parallel programming. So we can develop the parallel architecture or parallel processor or chip multiprocessors, multi-core architecture. What's the problem? So if there are multiple threads, there is no problem. But for the performance of the single application, this is a critical problem. So what's that? Oops. Parallel software is the problem. So how can we design this parallel software? Let's change it. So this expectation. If we use the multiple cores, then performance will be increased proportional to the number of cores, and then that's our expectation, and then also customers' expectation to who buy the multi-core processors. Well, it's not true. It's not true in the real world. Also, this is the expectation of the bosses, but it's not true. It's the expectation of the company owner. That's not true. So we have to get significant performance improvement for the single thread application, but that's not true. It's not possible. So if we want some high performance or high performance for the single thread application, then what's our choice? We can use the faster single core processor because it's easier. Actually, that is the performance of the single application, but it actually and then but on the modern actually recent situation, the computer runs the multiple thread or multiple processes, so multi-core architecture is good. It has some benefit to run some modern applications. So these are some challenges: partitioning, coordination, or communication overhead. So as I said, communication burden prevent some scalability of the computer system or computer core or our real world. So let's see the Amdahl's law. Amdahl's law is very important, and then this Amdahl's actually very simple. So very simple. Most of the law in the computer architecture is very simple, but these laws give us some intuition about some better computer hardware or better computer systems or some economical situation. So what is another popular law we learned in this course? Moore's law. So Moore's law is very simple. So you need to actually it's some common sense and of the computer science or computer engineering students. And the Moore's law is just some economical law in the computer industry. Amdahl's law is just a very simple law, and then I believe the elementary students can understand this law. But this Amdahl's law gives us a very important intuition of the parallel processors. So let's see what Amdahl's law is. So Amdahl's law, Amdahl's law says that sequential part of application can limit speed up of parallel processors. That is what Amdahl's law says to the researchers or some normal people. Okay, so let's see what Amdahl's law is. So so this is some workload of the application, but we can classify this workload as the sequential part. So this is the sequential part. So what is the sequential part? The workload cannot be parallelized. So that means that this workload should be executed sequentially. And then some part of workload can be parallelized. This is the parallelizable part of the workload. So if we apply the multi-core architecture or parallel processors, we cannot improve this part, the sequential part, because the workload cannot be split into multiple parts. But we can improve only this parallel part. But how about the entire performance improvement? This part determines the entire performance improvement. That is what Amdahl's law says to us. Actually, this is true in the real world also. That's why the Amdahl's law is very simple. So let's see this example. So this example, so it's the 100 processors, 100 parallel processors, and then we want the 90 times of speed up. So that means that the execution time is reduced to the what's that? So 90 times should, that means that it's the t new is a time, and then this is the t old. So if the computer system is improvement, then the execution time is reduced. This is the t new, and then the t old is divided by the t new, then the speed up should be 90. That's our expectation. So both commands are that. So you can make the 100 cores. You can use the 100 cores, but I want 90 times of speed up to make the computer system or make some software. How can you make? So first, we can divide. We need to divide our workload into the sequential part or parallelizable part. So this parallelizable part can be reduced by the execution time of the parallelizable part can be reduced by the multiple cores. So if we use the 100 cores, then what is the execution time of the parallelizable part? This is some simple assumption, but we think that this parallelizable part can be split into any numbers. So it's divided by 100. And then we cannot reduce the execution time of the sequential part. So this is the execution time of the new computer system. Then what is the speed up? So let us assume that the fraction of the parallelizable part is the f parallelizable. Then 1 minus f is the fraction of sequential part, obviously, right? And then this parallelizable part can be divided by 100. So that is the actually new execution time. And then actually here is the t old here, and then this is the t old. So this is the t old multiplied by 1 minus f parallelizable, and then plus f parallelizable divided by 100 multiplied by t old. That is the t new, the execution time of the new computer system. Actually t old is the 1. So this is the this t old can be removed. So this is the speed up of the parallel computer system. Then should be 90, right? So how can you can solve this equation easily? So it's elementary mathematics. So what is the f? F is the 0.999. So that means that the software, the workload can have the 99.9% of parallelizable part. If the workload has the this characteristics, that is very good situation. But normally the workload has the actually the large fraction of It depends on the characteristics of applications. But if the application has this some large fraction of the parallelizable part, then that is very good. So only sequential part should be 0.1% of the original time. It's just the purely parallelizable application. So Amdahl's law said that. So if this part increases, then the speed up should be significantly reduced. So we cannot meet the expectation of the boss or some company owner in this case. But with the Amdahl's law, that is obvious. So this is the example. So this example is the workload is composed of sum of 10 scalars and then 10 by 10 matrix sum. So we know that this part is the parallelizable part, and then what's that? This is the sequential part, the 10 scalar. We just compare the 10 multiple processors and then 100 multiple processors. This is the execution time of the single processor. The time is the 10 plus 100 because the number of elements of this matrix is the 100, and then multiply by delay of the adder. So this is the single core processor's execution time. How about the 10 processor? We can reduce this part only. Divide this part with the number of processors, then it's the 20 T add. So what is the speed up? In the original computer system, the execution time is the 110, but with the 10 processors configuration, then the execution time is the 20 T add. So speed up is the 5.5. So with the 10 processors, this is the expectation of the normal people who doesn't know about the Amdahl's law. Then what is their expectation? The speed up should be 10 because we invest the 10 independent cores. So that means that there are 10 workers, and the normal people expect that the performance of the 10 workers should be 10 times of the single person. But as you can see, this is just 5.5. So that is the 55% of the potential. This is the some ideal case, and then some normal people's expectation. How about the 100 processors? But this workload can be parallelizable. So divided by 100. So execution time is the 11 T add. What's that? So speed up is just 10. So 10% of the expectation is the potential. so that's very low. Why? The application has sequential part, and then actually this sequential part is less than 10% of the entire workload, but because of this sequential part, the performance improvement is limited or saturated. But the good thing is that we can increase the size of parallelizable part. So we can actually increase the size of application or software. So if we can increase the matrix size is the 100 by 100, then this parallel part is increased. The workload size is increased. Then what's that? With the 10 processors, the speed up is 9.9. That is the 99% of the potential. Potential is the 10, the expectation of the normal people. And then with the 100 processors, the speed up is the 91%. It's the 91% of the potential. So this example shows me that if we can increase the size of parallelizable part of our equation, our application, then this application can benefit from multi-core architecture or parallel processors. That is what Amdahl's law says to us. Okay. So actually, Amdahl's law is based on the strong scaling. So strong scaling, with the strong scaling, we assume that the problem size is fixed. So that means that the application, so we cannot modify the application or some application data. So this is the example I already showed. So with the weak scaling, the problem size is proportional to the number of processors. So with the weak scaling, software develop, so we can use some larger size of software which has the larger fraction of parallelizable part. So actually, this strong scaling has some assumption that the software is not developed. The software engineer does not modify the software for some parallel processors. So workload size remains the same, but that's not true also. So when the multi-core processor is introduced in the real world, the software is also changes to support these multi-core processors. So and then so software is also the structure of application or structure of software is also modified, changed by the software engineers. That's actually obvious change. So in the history of the computer system, so we cannot separate the development of the software and then development of the hardware. So good hardware cause the better software, and then better software also requires better hardware. So this is some cycle between hardware and software. And then let's see some instruction and data stream. So this is some classification of the processors. So we can classify the processors with some type of the instruction and then the type of the data stream. So what's this type of instruction streams? Single and multiple. That means single instruction and then multiple instruction. How about the data? Also, we can classify the data as single and multiple. So based on this criteria, we can classify our processor as the single instruction, single data, or single instruction, multiple data, such as. So there are two classification for the instruction stream, and then two categories for the data stream. So what's the possible combinations? 4. 2 by 2. 2 multiplied by 2 is 4. So with this type of instruction and then with this type of data, we can make the 4 different types of processors. So let's see the SISD, single instruction and single data. That's what we learned in this course actually. So an example of this SISD is the Intel Pentium 4. And then what we learned until now. So single core processor. How about the SIMD? This is called the SIMD. That's actually SISD is not popular because it's just a normal processor, normal single core processor, and then also it is not easy to pronunciate. So SISD it's not easy to pronunciate, but SIMD is good. So we frequently calls the SIMD as the SIMD architecture. So SIMD architecture is the single instruction and multiple data. What does that mean? With a single instruction like add, but this add instruction use the multiple data, like a vector type data. So this is the SIMD architecture. So that is the example of the SIMD architecture, SSE instruction of the x86. So if you, so actually SSE was very popular in the previous decades, but SSD is the it's the basic part of the modern CPUs, and then this SSD is the essential for running multimedia applications, right? So if the processor does not support the SSC instructions, then the older processor, it was very hard to run MP3 applications. That's true. So if we launch some MP3 application, then the computer does not run smoothly. Did not run smoothly in the old computer system. It's because it's very hard to process the multiple data of these multimedia applications. But how about the modern computer system? MP3 runs very smoothly on the modern computer system, like even in the smartphone. Even on the video application runs very smoothly on the smartphone. Is because these applications support the SIMD type instructions, like for multimedia application. We can make the MISD, multiple instruction and single data, but it's not reasonable. Why? So multiple instruction, single data is not reasonable. And then MIMD is a multiple instruction, multiple data. It's just the independent thread runs on the independent core. It's the multi-core architecture, the chip multiprocessors such as the Intel Xeon. So we can classify the type of processors with some type of instruction stream and then type of data streams. Okay. So let's talk about the vector processors. So actually, in the previous slide, I mentioned the vector processor when I explained about the SIMD architecture. So it's a highly pipelined functional unit. So what's the vector architecture, vector processor? So vector processor supports the SIMD type instructions like a vector add, and then this vector add instruction use the vector type operands such as the v1, v2, or v3. So this vector type operand has the multiple elements. That's true actually. In the vector type, this one single vector includes the multiple instructions, multiple data, multiple elements. So how this vector processor works? For example, this add instruction, the add has like a floating point add instruction. Let us assume that the type of element of this vector type operand is the floating point data, and then so VAdd need to support the floating point add operation, and then for this add functional unit like a adder, the hardware adder can be pipelined, like a highly pipelined. So that means that the element 1 of this B2 and B3 is executed in the first stage of the add hardware, and then on the next clock, element 1 is executed by the second stage of the adder hardware, floating point adder. So with this similar fashion, the execution of this vector add can be pipelined. So with the vector processor, the functional unit has functional units are highly pipelined. So with this highly pipelined functional units, the vector processor execute some arithmetic operations on the vector type data. So the multiple elements are step by step executed on the multiple stage of the functional unit, step by step in every clocks. So RISC-V also supports the vector extension. So we did not run in this course. And then RISC-V also supports the vector type register file. So that is the optional. So actually the RISC-V has the many extensions. If you add some functions, then you can apply some extension of the RISC-V. That is the vector extension. So and then this vector extension supports the vector instructions like vector load and the vector store and the vector add, vector add, and then vector scalar and add. Interesting. So this is the example of the conventional assembly code, and then it's some vector type assembly code that use the vector type instructions. Okay, as you can see, in order to calculate the vector operation, then we need the iterative loop. That's true. So this is the array calculation, and then if we want to calculate some array operation, then what's that? For I equals 0, I is less than number of element, and I plus plus a I equal b I plus ci. That's how we use the scalar instructions for array operation. But how about the vector operation? So for the with the vector instruction or vector processors, we do not require this iterative loop, because the elements are grouped into a vector type operand, and then these grouped elements are stored in the vector register. So like this. So here is this is the vector register, and then the vector registers are executed with the vector instructions. So this is the vector load. So based on this base address, the elements of the vector type operands are stored in the vector register V0, and then the vector scalar multiply. So this element of the vector register is multiplied by the scalar operand like F0, and then it is also stored in the vector type register. So what is different? So in this example, there is the loop, iterative loop, and then this iterative loop is executed some n times, and where the n is the number of elements in the vector. So it's repeatedly executed. But with the vector type instruction, the vector instruction is just executed. The size of instruction is reduced. Also, the control part is removed from our assembly code. So program is more simple. That's the good part of the vector processor. Also, as the control part is removed, then what's that? We can reduce the performance degradation by this control instructions, like control hazard. So we can reduce the control hazard with the vector type instructions. So, but the compiler needs to support this vector processor require the support from compilers. So it's the vector architecture, and then compiler assigns the data to the vector type registers. So and then compiler need to generate some code using the vector instructions. So and then, as I said, the iterative loop can be removed from the assembly code, and it's the good advantage of the vector processors. Also, with the vector instructions, the data is regularly accessed, and then that is also, if the data is regularly accessed, we can improve the performance of processors, and that is also a good thing. So, like for example, the vector load f load dot v. So it's just some regularly aligned fetch the regularly aligned data from the main memory, and then when the data is regularly aligned in the memory, and then it's fetched from the main memory, and with the burst mode, so it's called the burst mode, then the performance can be improved. So we can reduce the control hazard. And so, but these vector type instructions are good for the multimedia applications, because the multimedia application, such as the audio or video applications, use the matrix or vector type data. So, for example, in the video application, actually every pixel has its own value, but we know that the pixels are regularly aligned on the screen, like some frame of the data, and then so this for the video processing application, this regularly aligned data can be executed by the vector instructions. And then the SIMD is also similar to the vector processors, and then SIMD is just what is the SIMD? The single instruction and multiple data. Actually, the vector instruction has the SIMD type. SIMD has the SIMD type instructions, like a single instruction, like a vector add, and then multiple data, the multiple elements inside of a vector. So this SIMD processors is used for also the multimedia applications, like MMX or SSC instructions in x86. So actually this is very popular, and then that is the essential part of the modern CPU, because the modern CPU also support the multimedia applications. That is essential part. So with this MMX or SSC extension of the x86, multiple data elements can be stored, and then the size of the register is the 128 bits. So with this SIMD type processor, then we can also simplify the structure of the assembly code. Also, as I explained, we can reduce the hazard by control instructions. And then this type of processor is good for the multimedia applications. Then let's talk about the hardware multithreading. But what is the hardware multithreading? Multiple thread runs in a single core. That is called the multithreading. And then we are also very familiar with this multithreading. What is the most popular multithreading in the processor? Hyperthreading by Intel. So actually, when you see some number of threads of the Intel Core processor, like for example i7. So actually, in the previous generation of the i5, actually the i7 does not support the hyperthreading, but recently the i7 also supports the hyperthreading. But let's take the example of the i7. So when you see the specification of the i7 processor, then you can find the number of cores and then number of thread. So in the i7 processor, let us assume that the i7 has the 6 cores, but number of threads supported by these 6 cores is the 12 concurrent thread. So what does that mean? 2 threads are concurrently assigned to the 1 core. So actually until now we learned about some simple core, is a pipeline core, and then in the pipeline core only 1 thread can be assigned. But what's that mean? The 2 threads are assigned to a single core. That is called the multi-threading. So multi-threading is that performing multiple threads in the single core, and then for this multi-threading, the single core has the multiple sets of the register file. Also, the single core has the some separated instruction fetch unit. So the instruction is fetched from the separated thread, and then in order to support this multi-threading, the processor switched the execution of the one thread to the another thread very quickly, and this is called the context switching. The context switching is that change from one thread execution to the another thread execution. So there are 2 types of this context switching. The fine-grained multi-threading is a switch performs the context switching every clock, and then coarse-grained multi-threading. So this coarse-grained multi-threading, the context switch happens when the one thread is encounters the cache miss. If the thread encounters cache miss, then it should wait a long time because until the data is ready from the low-level cache or main memory. So while the one thread is waiting for this fetch data from the memory, then this one thread should be stored in the processor. Then that is some waste of the processor resource. Then processor switch to the another thread and then execute this thread. This is called the coarse-grained multi-thread. So this coarse-grained multi-thread is simpler than the fine-grained multi-threading, but with the coarse-grained multi-threading, we cannot hide the data hazard by some short data hazard in the single thread. Okay, but what's the advantage of fine-grained multi-threading? The context is switched every time, so we can reduce some effect of the data hazard of the single thread. Also, there are some advanced technology. It's called the simultaneous multi-threading. So actually, the hyper-threading of Intel is the simultaneous multi-threading. So simultaneous multi-threading is that there are multiple slots for the instruction, and then this multiple slots is filled by the multiple thread. For example, if the Intel core has the 4 multiple slots for the instruction, then these 4 instruction slots can be shared by multiple thread. So the fetch engine just the instruction from the multiple thread, and then fill this multiple slots for instructions. But modern processor has the enough number of functional units, so these multiple instructions can be executed in parallel. So actually, it is better to see this concept of coarse multi-threading, and then fine multi-threading, and then simultaneous multi-threading. In the coarse multi-thread, this is some concept execution of the thread A, thread B, and thread C, and thread D, and this is the clock, the time. So in the thread A, there is no instruction between this clock and this clock because this instruction encounters the cache miss, so no instruction can be executed after this clock cycle. So this coarse multithreading, if the one thread encounters the cache miss, then the CPU switches to the another available thread, like a thread B, and thread B is executed until the thread B encounters cache miss. And then fine-grained multithreading, the thread is switched every cycle, like from the thread A, and thread B, C, D, and then A, B, C, D. But the instruction slots are not filled. Some instruction slots are empty. Okay, but simultaneous multithreading, there are some hardware instruction slots. Instruction slots are filled by some available instruction of the available thread. So there are 4 instruction slots in the SMT. The 2 instructions are filled by thread A, but there two slots are empty. These empty 2 slots are filled by 2 instructions from thread B. That is the simultaneous multithreading. So as you can see, the performance of the simultaneous multithreading is best compared to the coarse multithreading or fine multithreading, because the hardwares are utilized without some empty instruction slots. The problem is power. So in order to support this simultaneous multithreading, the structure of the processor gets more complex and more complicated. So that means that more power is consumed by the simultaneous multithreading. So instead of using this simultaneous multithreading, it may be good to use the more simple cores. So that is some trade-off between more cores, more simple cores, and then smaller complex cores. Okay. Okay, so I will stop here, and then I will talk about the graphics processing unit next class, and then I will conclude this course. 네, 수고 많았습니다. 사실 뭐 이런 멀티프로세서를 약간 브리플리 다루고 있는데, 뭐 이 정도 이제 뭐 이 코र्스에서는 뭐 이 정도 알아놓으면은 뭐 충분합니다. 그렇지만 이런 컨셉이라든지 이런 클래시피케이션 이런 부분들은 뭐 잘 알아두는 것이 이제 좋습니다. 왜냐면 우리가 이제 컴퓨터 사이언스를 전공하는 학생들인데, 뭐 멀티트레딩이 시뮬테니어스 멀티트레딩이 뭔지, 아니면 뭐 CMD가 뭔지 이 정도는 알아야죠. 네, 알아야 됩니다. 상식적으로. 네, 그러니까는 뭐 어쨌든 시험에는 다 나올 거예요. 시험에는 다 나올 거기 때문에 잘 공부를 해주시기 바랍니다. 예, 수고 많았습니다. 다음에 이제 뵙겠습니다.